All right, got a good question here about number 45, and always a tough one here, because remember this, the buoyant force is equal to the weight of the displaced fluid. And that's really the key to all these buoyant force ones, although changing that phrase into mathematics can be a little challenging. And in fact, I just posted one from what had some numbers in there, number 23. So you might want to look at that copper one. But this is the idea, and this is a conceptual one here. But it simply says this: it tells us that salt water is a little more dense than fresh water. Will a 50-ton ship feel a greater buoyant force floating on the freshwater lake or on the ocean, which is, of course, salt water? Now, kind of a quick but wrong guess would be say, yes, they are different. And that's where you can run into troubles, because if your mind is thinking that maybe this is the ship, okay, and so here's the ship in, say, freshwater, and so this is the part of the ship that is below the water line. This is the water line. And then you compare it maybe to salt water, so fresh, salt. And if in your mind, if you're still thinking about the ship being just as deep, just as long, you are going to say, well, it's the same volume being displaced, but the density of the salt water is more, hence it weighs more, hence it's a greater buoyancy force. And there is where the problem is. It's not the same volume. To give you an idea, here's what would end up happening. Let's just say you could start with a lake of fresh water, and then all of a sudden, magically, boom, you change it all to salt water. See, that would, right at that moment, make this a greater buoyant force, because, again, at that moment, it would have been the same volume, but given the greater density of the salt water, it would be a greater buoyant force. But here's the interesting thing. Let's go back to the freshwater. See, the freshwater, when the ship was floating here, you had a downward force equal to the weight of the ship, mg, and an upward force exactly equal to the buoyancy. If all of a sudden you magically went from freshwater to saltwater, this buoyant force, and I'll draw it with a little taller arrowhead, would turn bigger and would actually be bigger than the weight. And as a result of that, it would actually push the ship up. And of course, as it pushes the ship up, it's displacing less water, and therefore this buoyant force would go down. And what would end up happening, it would go down until it's at equilibrium again, until the buoyant force is equal to the weight. So a better picture in your mind of what is happening, if this is the water level, and the fresh water looks like this, so it's displacing this much volume of fresh water. Then if this is the water level in salt water, as I said, it would actually go and displace less. What we would say is the ship would sink less. It would have, I think they call this the draft of the ship. And so it wouldn't go as far underwater. And so maybe in a freshwater lake, maybe you have a draft of 8 feet, but then you get into this saltwater and you have a draft of 7 feet. But the real key to this was to realize back here with our free body diagrams of Newton's second law, so it goes back a few chapters, but incorporating forces with this new force called a buoyant force, and our old forces with gravity, what would end up happening is you would reach a balance point when the buoyant force pushing up is equal to the weight pushing down. So I'll say it again. If you could just magically switch from freshwater to saltwater, yes, then the buoyant force would be greater. But what happens is it would then push the ship up, And as it is displacing less, the buoyant force would be going down, and the buoyant force would go down until it was again equal to the weight of the ship. So the answer to this problem is the buoyant force would be equal to the weight of the ship, regardless of whether it's in freshwater or saltwater. Now, again, there's a difference between freshwater and saltwater, and of course the difference in saltwater is the depth into the water. The draft of the boat would be less, so that you have less volume, but you have more density, and then the two together give you the same weight, which would be the weight of the ship. So the answer is anything that's floating, its buoyant force is equal to its weight. So this one was talking about a 50-ton ship. So that's how much the ship weighs. That means when it's in fresh water, it displays 50 tons of fresh water. When it's in salt water, it also displaces 50 tons of salt water. It's just 50 tons of salt water is a lower volume than 50 tons of fresh water. So that's the idea of this problem.